So let's see what happens on the pole where x1 plus x2 plus x3 is 0. Okay? When x1 plus x2 plus x3 is 0, what I'm left with upstairs is y1 plus x2 plus y2. Right? That cancels that. Okay? And what I'm left with is these 4 poles. And so what is this? This has y2 in it, that has y2 in it. This is y2 plus x1 plus x2, and this is y2 minus x1 plus x minus x2. So these two combine into a propagator. And similarly, these two combine into a propagator. So that's how we get the scattering amplitude. Okay? So it's important that the numerator killed the one extra propagator, and we get the scattering amplitude. Okay, what about this guy? How about this guy? Well, that's not so recognizable now. So now let's sit at x1 plus x2 equals 0. Now, well, something's combined into propagators, some not obvious, right? What do you think that is? Well, see, the reason at loop level, these y's are the magnitude of the spatial momenta that are running in the loop. So this thing could not have been the loop integrand because it doesn't depend on L0, L1, L2, L3. There's no L0. It only depends on the spatial momenta. Okay? So it's a priori not obvious how we should recognize this as being related to the actual loop integrand. Okay? Except there's only one thing it could possibly be. How do I get rid of L0? I mean, this whole problem is not relativistic, right? Right? Fundamentally is not relativistic, it's not Lorentz invariant. So of course it shouldn't have the L0 in it. It only has the spatial L's. But there's only one reasonable way to get rid of L0. Do the L0 integral on the Feynman I epsilon. Okay? That's the Feynman tree theorem prescription. And we don't do it in field theory because we like Lorentz invariance a lot. But it's completely canonical to do. Just do the L0 integral. And you can do it in various ways. You can close the contour upstairs and close the contour downstairs. But when you do the L0 integral, you get a new integrand that only depends on spatial momenta. It's exactly this one. Okay?
So you get like an effective non-relativistic theory, like NR3D or NR3C.
Well, except it's really a relativistic theory and not in great disguise. Okay? It's not fundamentally relativistic. You see it's not relativistic, but for trees on the pole where you should turn into the scattering amplitude, all these poles combine and turn into propagators, relativistic propagators. And at loops, what you get on the pole is the representation of the loop integrand after you do the L0 integral on using the Feynman I epsilon. So that's the point I wanted to make. Okay. So now you know the first definition in terms of the time integral. The second, the related computation in terms of old-fashioned perturbation theory. And the clues that it has to do with some polytopes, and I've even drawn some shapes to go along with them. And we've seen how the amplitude facet is, how the pole that reveals the amplitude does its job. So yeah.
Right. Because it doesn't seem to be a sum of two terms. Or is there some?
Maybe there's some twos. Let me try to remember. Does anyone? Huh? I think it's correct. I think it's correct.
Well,
Yeah.
why is it not a sum of two terms then? Because it seems like they're triangulated.
Hmm?
As a sum of two. You can triangulate it as a difference of two terms, right? But
No, this is not a difference of two terms. So no. This is the triangulation of the dual. Okay. So this is the polytope itself. But these local formulas are like the triangulation of the dual. Okay? The dual of this looks like the ordinary cyclic, looks like that. Okay? And so this formula is the sum of two terms. That's the sum of those two tetrahedra for the
But
dual.
how do you turn that one line to sum of two terms?
You raise the numerator and just
The
put the
numerator.
the last two denominator, you fraction.
It's right there are these. So there is some 1/2.
Yeah. No. There might be a.
overall two in the numerator.
There is some overall. Okay.
Yeah, they're overall twos. I'm not keeping track of overall twos. Yeah. Right. Sorry. Yeah. Right. Yeah. That's right. Yeah. Yeah. There's probably an overall two. Anyway. Okay. So now let me tell you what the object is. And I'm actually going to do it in the most, starting from the most invariant definition of what it is. You see here, so a big weakness of this story that is graph by graph. Okay? So it's, I'm going to tell you something for each graph. We don't yet have a story for combining all the graphs together. Already even for this phi cube theory, finding that analog is like finding the isosahedron. Okay? So this is like individual cubic graphs, and putting them all together for amplitudes for a simple scalar theories gives you something like the isosahedron. And so we would love to find an analog. So instead of a kind of a simplex for each graph, we have something much richer. And then on top of that, we want to find some structure that will put them all together. So we don't have the second thing yet, but so let's just talk about this graph by graph story.
But you're not saying it's phi cube, right?
It doesn't have to be, but it could be. It could be phi cubed, right? You could, I could make this, yes. And anyway, I was just talking about trees for that statement for now anyway. Yeah. Okay. So now let me give the definition of these cosmological polytopes. And we're going to begin by thinking about a world with a bunch of triangles. Okay, a bunch of triangles, A, B, C, A1, B1, C1, A2, B2, C2, and they each live in their own private spaces. Okay, so they're not all, I'm drawing in the same two-dimensional space, so they're all in different spaces. Okay? So this space is pretty boring. So we're going to make life more interesting by allowing these triangles to intersect each other. Okay? But every triangle ABC of this sort is going to have two sides that are friendly and one side that's unfriendly. And what that means is that the friendly side is going to allow other triangles to intersect on that edge with it, and the unfriendly side it won't. So this is a funny rule. First of all, we're talking about triangles, so there's a 3 in the problem, but the 3 are not treated symmetrically. 2 of them are similar and 1 of them is different. Okay? Now, so in more detail, then, so we have each one of these. The friendly sides, we're going to mark a midpoint on those sides where they're allowed to intersect with other triangles. And on the unfriendly sides, we don't. So we put another mark there to remind ourselves that we can't intersect there. Okay? So if they intersect, it means that A plus B, so if this is ABC, A plus B for one triangle is allowed to equal A prime plus B prime for another triangle. Right? If I really think of them as sort of vectors, saying that they're allowed to intersect at their midpoint means that A plus B can equal A prime plus B prime. And B plus C is allowed to equal B prime plus C prime. These are allowed. They're not compulsory, but they're allowed. But we cannot have A plus C equals A prime plus C prime is forbidden. Okay? That's it. That's the definition of cosmological polytopes. Okay? You take any collection of triangles, you allow them to intersect on midpoints where two sides are friendly and the other sides are unfriendly. And then you just ask the whole picture to be connected, so you don't have disconnected pieces. Okay? Now, a moment's thought. So we're done. From this point on, everything is exposition. Okay? So the claim is that these objects, the canonical forms associated with these objects, calculate the wave function. Not obvious at all, but they're, just like the amplituhedron has this strange definition, C dot Z, positive flips. This has the same kind of rough flavor, right? There's some strange looking combinatorial construction, and we're really done. Now we're done with the rules. The rest is exposition. So let's see how it works. First of all, I didn't say anything about a graph. So first of all, how is this associated with a graph? Well, it's associated with a graph for kind of a cool reason, an obvious reason, which exactly has to do with this two friendly, one unfriendly business. Okay? So we're going to just graphically represent every triangle by an edge. So a triangle, I'm going to represent as an edge. Another triangle, before I allow them to meet or not, I'm going to represent with some other edge, another edge, another edge, and so on. Okay? And now, if two triangles meet on one of their two friendly sides, then I connect them on that vertex. So, I could take this one and I connect it there. So now it turned into that one. Then I can take this one and maybe connect it there. That's a friendly edge. It's allowed to do that. So I put it there. And I take this one and I connect it here. Okay? So each triangle is represented by an edge, and I glue the edges together to make a graph. So that's kind of cool. It's a dual perspective on graphs. Often you think about graphs as a collection of vertices connected by edges. This is the other way around. This is a collection of edges that are glued together on the vertices. Okay? Okay? So first of all, that's why it's associated with a graph. So any way of gluing these triangles together actually gives you a picture that's associated with a graph. All right?
So what's the difference on that slide for loop or tree?
Nothing. Nothing. Yeah. You just keep, yeah, there's no difference between loops and trees here. Okay? The only difference comes when you want to interpret the y's. These are just numbers. If you want to interpret them as a magnitude of vectors that you associated with the thing, then when there's closed loops, they're not determined by momentum conservation. So it's the usual logic. But at this level, there's no difference. Okay. So let's already see what do some of the examples look like. So already, just this guy is just a triangle, nothing else. Okay, just one triangle. What is this guy? This is a triangle. These are two triangles that meet on one of their friendly edges. So if I draw that friendly edge for one of them, it looks like that. And the third vertex is off somewhere in some dimension. The other friendly edge looks like that, so they meet at their common, this is their midpoint, But these are the two edges of one triangle, so that's one triangle. And this is the other one. They meet at their midpoint. So this is another one. So because these things meet, these four guys are in a two-plane together. But this edge is in its own third dimension, and this edge is in its own fourth dimension. Okay, so that's that double square pyramid that we talked about before. Okay? And finally, let's do this one. This one's more interesting. This is one triangle. Okay? And there's another triangle, and they actually meet on both of these edges. Okay? So let me go back to this picture. It's easier to draw the picture. Okay? So here is one triangle on one end, and here is the other triangle. Okay? So those are two triangles, and they meet at these are the friendly midpoints that they meet on. Okay?
So when you take convex hull, you don't consider any midpoint?
No, I only take the convex hull of the points on the triangle. That's very, very important. Okay? So in fact, we are now just going to give the rule in general. Now that we see that it's associated with a graph, we can actually very nicely give a rule. So it's natural to label these triangles. It's natural to label these triangles by, again, this is the unfriendly side and the two friendly sides. So for any given triangle, remember, we're associated with some edge in a graph, so it has an E and a V and a V prime. So I'm just going to label the midpoint by some vector x, v. So these are not numbers. These are kind of like unit vectors in the space. So I can put a hat on them to remind you of that. This is x hat v prime. This one is, I'm going to label with some y hat e to remind me that it's the unfriendly one. And so these vertices, which are the actual vertices of the triangle in terms of these ones that are not, this one is x plus x prime minus y. This one is x plus y minus x prime. And this is x prime plus y minus x. And I can put a hat on top of everything to remind me that these are vectors. I won't keep doing it. But I'm doing it because in a moment we'll also introduce variables associated with them. Okay, so all right, so now we have a concrete rule for what the vertices of this polytope are. Okay, so first of all, what is the dimensionality of the space? What space does the polytope live in? It lives in, so given any graph, given G, with E edges and V vertices, our cosmological polytope lives in the projective space of E plus V minus 1. Okay, so, but it's really just E plus V dimensional vectors. Okay? There are a bunch of basis vectors in the space that are associated with the x hats of the V's and the y hats of the edges. And it's therefore natural to introduce some point in this space, a big vector, EI, which is just the sum of some variables xv, x hat, plus ye, y hat. Okay? So that's just the coordinates, okay? Just the coordinates in this space. Okay, so each one of these x hat and so on are just 1, 0, 0, 0, 1, 0, and so on. And so this big energy vector E, it's like the y of the amplituhedron, is just the list of all these variables. So these are going to be the variables that showed up in our function. Okay, so E labels a point in this big projective space. I've just given coordinates in this big projective space. But associated with the graph, with every edge of the graph, with every edge E of the graph, with every E, V, and V prime, there was a triangle. There's a triplet of points. There's a triangle exactly given by the one that I drew. X plus x prime minus y, x plus y minus x prime, and x prime plus y minus x. Okay? So, if these are basis vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1, these are vectors that look like 1, 1, minus 1, 1, 1, minus 1, and so on in all the entries. Okay? Is that clear? Okay. So given any graph, there's all these points, and the cosmological polytope is the convex hull of these 3 E points. Okay? And finally, the canonical form for the cosmological polytope associated with the graph G. And E is E d edge E minus V minus 1E exactly times that function of G that we talked about of X and Y. Okay, so that's exactly the relationship, just like with the amplitudes and the amplituhedron. Yes?
Just in the picture before.
Yes?
Maybe you said it, I just missed it. So you don't allow any tadpoles? Tadpoles.
You can do anything.
Well, what is just the tadpole then? It has two variables, right?
What is just the tadpole?
Or for example, just tadpole or taking your line segment and put tadpoles at the end. Because it's just adding one variable, right? Maybe you don't allow that.
I don't think they're a problem, but let me let's ignore them for now. Yeah, it's I think they're like they kind of trivially factor into it, but yeah, sorry. Let's just ignore tadpoles for now. Sorry. Okay. So that's the construction. That's now. Now I want to say one more conceptual, qualitative thing about this, which is, I think this is pretty amazing. We start with a bunch of intersecting triangles, two friendly, one unfriendly side. We let them interact in every way they can to make, which is associated with a graph, and that gives you a polytope. The canonical form of the polytope calculates the wave function. That's out of this object comes a scattering amplitude. Out of this object comes all sorts of stuff. So where is the magic? Where is it coming from? Right? It obviously has something to do with this funny business of two friendly, one unfriendly side, and the intersecting on midpoints. And I want to point out what this reminds one of. What does this thing remind us of? Of something that some threeness where two are similar but not identical and one is different. This is exactly the picture of space-time. Okay? Light cones. Okay? It's exactly the picture of space-time where we have future, past, and space-like separated. And this is not a joke in this context. In fact, that is exactly where it comes from. Okay? First of all, this future, past, and space-like is the origin of that plus, 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 minus, the plus, plus, minus form of the propagator. Okay? But in much more detail, when you study how this thing works, that's exactly what this two friendly and one unfriendly side is doing. Okay? Anyway, I can explain a little bit more how this is more than just a a vague coincidence. But this business is what's inputting the most basic physics of causality into this combinatorial game. That then kind of turns into the real thing. Okay. So let me just say a few things, a few final things about this. So we begin with this description, with this primitive description in terms of triangles. These are the vertices of the cosmological polytope, and they all have this x plus x minus y, x plus y minus x type structure. Now, if you remember, we saw what the poles of the form look like. The poles of the form look like they're associated with this way of breaking the graph into subgraphs, right? So that means that the faces of the cosmological polytope have to somehow be about making connected subgraphs and adding the energies from the outside and all of that. Okay, and in fact, you can derive the facet structure of the whole cosmological polytope and what the faces actually are. And it's somewhat remarkable to see this picture of making connected subgraphs and adding the energies from the outside and all of that actually arise from this definition fundamentally. Okay, so I won't go through it now, but there's a section of our paper where we describe in detail how that works. Okay, it's very simple, but I mean it's not a priori obvious that starting from this definition with 3E things in this triangle that you should get these energy denominators that have to do with connected subgraphs and so on. But that, of course, that's also something that comes out. A few other things. As with polytopes for amplitudes, these are just polytopes. They're not fancy amplitahedra. They're just polytopes. But as we're used to with polytopes for amplitudes, a triangulations of the polytope itself give us one form of the amplitude. And in this case, if you directly triangulate the cosmological polytope, it's not directly related to the Feynman diagram expansion, but it's close to that. If you triangulate the dual of the polytope, that directly gives you this old-fashioned perturbation theory formula. One of the natural triangulations, but there are many of them. Okay, as Yara was saying before, if we look at this basic object, this guy, its dual looks like this. And so, for instance, we have a 2-term triangulation, which is old-fashioned perturbation theory, and a 3-term triangulation, which is not anything obvious. Okay.
What about CSW, like putting stars?
Yeah, they're all fine. None of them have a known physical interpretation. Okay. What else can I say about these things? It is easy to prove, very easy to prove on general, just from the structure, that if you have any tree diagram, the faces where the sum of the energy goes to 0, that face, the one that should correspond to a scattering amplitude, it's very easy to show that on that facet looks like a simplex. Okay? That's really great, because that facet looks like a simplex. There can be no numerator for the form. Upstairs, you just get a product of a bunch of factors, and it's very easy to see that in that product, there's always an even number of terms, and they group up into propagators. Okay? So that's kind of remarkable, because there's no e squared minus p squared anywhere in the problem fundamentally, but on the facet, it becomes Lorentz invariant, as it has to. But again, you see, this is, I think, the first time that I've seen, it's a very, very toy example, but even something that has the flavor of Lorentz invariance coming out where it's not being put in. Okay, so the object is not Lorentz invariant, but where it's supposed to become Lorentz invariant, it does in this interesting way of doubling up the poles. When you have a loop diagram, when you go to the facet where the sum of the energies goes to 0, it is not a simplex in general, and it gets more and more complicated the more and more loops there are. And that's something that we didn't understand for a long time, but we've understood recently. I might talk about it a little bit at Amplitudes. But what happens, for example, at one loop, you go and it's a slightly more complicated object, and there's a variety of ways of triangulating it. Okay, you can triangulate it in, I think, 4 ways. If we take the maybe, I don't remember, 2 or 4 ways. But now there's something a little remarkable. This sum of energies goes to 0 face. On that face, every triangulation of this facet, we call it the amplitude facet. Every triangulation of the amplitude facet has a meaning. It corresponds to one way of doing the L0 integrals. One way of closing the contour is to do the L0 integrals. To go to the, sorry, that's right. So the amplitude facet at loop level is the polytope for the Feynman tree theorem. Okay? And indeed, there's many different ways of doing it, and as you go to higher and higher loops, there's more and more ways of closing it. But every way, and it goes both ways, every triangulation of the polytope corresponds to a way of closing the epsilons, and vice versa. Okay? So that's a fair amount of structure just on the stupid facet where the energies add up to 0. Okay? So I think this is interesting. You know, all of this structure comes from intersecting triangles. Okay? Which somehow has this most basic, primitive representation, combinatorial representation of space-time that you might hope for. Okay, so yeah, so I think that's all I'll say about it. We could go through some examples in more detail, but I think that's probably good enough for now. So maybe are there any questions? Yeah.
So you perhaps said it in the beginning.
Right.
So what is the exact proof that it has logarithmic singularities? Because just producing a bunch of poles, you can eventually.
Oh no, it's not. You mean what? Sorry.
If you go in the cut structure, in principle, you can hit double.
Oh sure. No. So no.
Can.
Huh?
Here you don't. In case.
Oh, no, here we don't, first of all. No, and then, so, I mean, as always, you check in many examples, and then you find the object, and then you show that for that object, one of the triangulations produces old-fashioned perturbation theory. And then you're done.
But in general, it doesn't have logarithmic, you are saying?
No, it does. It does. It always has logarithmic singularities, yeah.
But there is no, can you prove it? Because just
it's a canonical form of the cosmological polytope. That's how you prove it. Yeah,
Yeah, but the old-fashioned perturbation theory doesn't make that manifest.
No, but Feynman diagrams do more.
Okay.
Yeah.
Just
So
producing a bunch of poles.
no. Now, in fact, there's a little bit more to say about it. So one of the things, this was confusing for it obstructed seeing it for a little while, is one of the amusing things is that if you take residues just in x's and not the y's, then it's also true that the residues just in x's but not y's, they're all unit. Well, they just turn into the product of 1 over all the y's. Okay? So if you just take the residues in the x's, they are all equal, but you get the product of all the 1 over y's. So that makes it tempting to try to find a polytope just in x space. But in fact, it doesn't exist. And that's an example. I mean, it's not always true. Even if you find something with unit residues, it doesn't mean there has to be a geometry. In fact, what happens in this case is that it's kind of something like this. You know, I mean, it's sort of something like this. Okay, you can have a form with that has logarithmic singularities on these things separately, but it has this funny sum of overlapping pieces. In fact, it has that because in y space these things would have been separated, okay, and so you would take further residues and it's okay. But just in x's, they still have the interesting feature that they only have residues in y. That all the residues are uniform, but it's not logarithmic. Sorry, there isn't a polytope associated with it. a final thing I'll say about this is that here I didn't say any, I just immediately turned into this toy problem, doing this, computing this function and so on. Let me go back to the very start and tell you how you use this to actually calculate the actual wave function in the cosmological context. Okay? So remember here, I sort of pretended that all the couplings were time independent when I did all the integrals. Now, that's very easy to do, because if I go back to my initial problem, integral d eta d phi squared, and then I have some g3 of eta, phi cubed, and so on, then I'm just going to Fourier represent these guys. So if I Fourier represent these guys, each one of the g of etas I write as an integral d energy, e to the I energy eta, g tilde of energy. Then all I have to do is all of these factors were sitting there anyway in our formulas, right? So in order to find the actual answer, I have to take this function. In order to find the actual function, I have to integrate d energy, g tilde of energy, for all of the, for all the vertices of the problem, of the f that I had as a function of x vertex, and I shift all of the vertices by this energy, and the y's are left alone. Okay? Okay? Now, it's a very nice thing if we're doing like literally phi cubed theory in de Sitter space. Okay, so if this really corresponds to de Sitter and it's phi cubed in de Sitter. If I'm doing cubic graphs in de Sitter, this g tilde is just 1. And so I'm literally just integrating over the energies of f of x vertex plus e and y. Okay? So these are functions with a bunch of linear poles. They're canonical forms with linear poles. So what do you think you get when you integrate them, when you shift and you integrate them from 0 to infinity? You get polylogs. Right? So it's already interesting that even tree correlators in de Sitter are polylogs. Right? Even this 4-point function is a dialogue in de Sitter. That guy's already a nice, beautiful dialogue. This is a trilog. Okay?
So the number of integrations,
right?
Number of vertices.
The number of integrations is the number of vertices. So the degree of the transcendentality is just the number of vertices. Okay? Huh? Yes, it's uniform.
Why is it log?
Huh? Sorry?
Why is it log?
It's polylogs.
How do you know there aren't any instructions?
Oh, because these are just linear factors. These are trivial canonical forms for polytopes. Okay? In fact, these aren't just random polylogs. They're like Aomoto polylogarithms. They're sort of generalized Aomoto polylogarithms. Okay? But if you flat out try to calculate them, even for the dialogue, it's not that easy. For the trilog, it looks like a nightmare. Okay? However, the formula for the cosmological, the picture of the cosmological polytope actually gives you a one-line geometric formula for the symbol. Okay? Purely in terms of the geometry of the cosmological polytope. And and the formula has this very interesting character. Well, let me not describe it. I think it won't be easy to describe it. And so maybe I'll just mention that this is actually a slightly It's a very slightly more sophisticated example of standard Aomoto polylog. So what is an Aomoto polylog? Remember that we said that so what you can do is what you might like to do is take the canonical form for some polytope, y, and you might like to integrate it for y inside some other polytope. So if this is a canonical form for polytope P1, you might want to integrate it where y is inside some polytope P2. Okay? If you do this, you're going to get polylogs. Clearly, you just have integrating things with linear factors over other things bounded by linear regions. So this is going to give you some functions, some polylogarithmic functions that are a function of a pair of polytopes, P1 and P2. And in fact, there's a more symmetrical way of writing this, which is that we can think about this as I've already explained. So this is itself the integral over a dual polytope. So really we have some y dn y, w dn w over y dot w to the n plus 1, where w is inside the dual of polytope 1 and y is inside polytope 2. Okay? That's a very, very beautiful symmetrical formula. Okay? Now, Mr. Aomoto defined these for simplices. So if you have two separate simplices, there's a very nice formula. Well, it defines some polylogs, and there's a very nice formula for it.
There should be a compatibility condition.
Sorry?
There should be a compatibility condition. A condition for the.
No. I mean, to make life really easy, you can just start by imagining that they don't intersect each other at all. So one polytope lives here, one polytope lives there, and then you can define things by analytic continuation after that. Okay? So you don't want the singularities in the integration region and so on.
Right. The definition was written like to take a pair of admissible.
Yeah, admissible means that they shouldn't intersect too badly. Okay, so they're even allowed to intersect on they can intersect on vertices and so on. They can't intersect on too high a codimension. Okay, but just for this purpose, just imagine they don't even intersect at all, so you don't have to think about it. Okay, so in my paper with Alice Yuan, one of the things that we talked about is how to extend this picture for general polytopes. Of course, all you have to do is triangulate them and add them all up, right? But you'd like to have a more intrinsic understanding of what they are. And indeed, here is the understanding. So we like to characterize the polytope P1 by its vertices. So these have some vertices ZA, and the polytope P2 like to characterize the polytope P2 by its walls. So these would be some ZAI and some W alpha Y. So its walls or its faces. Okay? And then the formula for the symbol has the following. Then we have the notion of a walk that you can take on the polytope, okay? On each of the polytopes. So let's start with polytope P1. So let's imagine that P1 looked like this, just to give an example. So say this is P1, okay? And so this is the kind of walk that you do. You start from any vertex. So let's say I start from this vertex, okay? And I then imagine that I project the whole polytope through that point. Okay? After I project the whole polytope through that point, I go to one lower dimension. I have a one lower dimensional polytope. And that one lower dimensional polytope, who is it? It's the convex hull of all of the guys that were connected to this one by an edge. Okay? So after I project I have a one lower polytope. So if this is A, B, C, D, E, F. Okay, so I start with A. A is connected to B, C, E. A has gone to the origin now after the projection, so I have B, C, E. Okay? And then I repeat. Now I go to any vertex of this guy. So I go to B and I project through him, and it's whoever I can go to is C. Okay? So any walk of this sort. So for example, an admissible walk is A, B, C. That's one. A, B, E. That's another one. All right? Notice that I have B and E, despite the fact that B, E were not connected by an edge in the original polytope. Okay? So it's this thing where you go to the guys that you can connect, and then projecting through the guy that you started with, you now look at the new polytopes that you get, and you just keep going. So what are examples of things that are not connected? Anyway, there are some examples of things that are not connected in this picture. Okay? So in this way, we have some paths. We have a path which is some vertex v1, v2, v3, up to vn minus 1 at the end. Okay? If it's an n-dimensional, if we're in the n-dimensional projective space. Again, with the property that v2 is connected by an edge to v1, v3 is connected by an edge to v2 and the polytope projected through v1, v4 is connected to v3 and the polytope projected through v1 and v2, and so on. Okay? So this is a permissible path. There's also a permissible paths, so permissible path for the vertices. The permissible path for the walls is a set W1, W2 up to Wn minus 1 with the dual property. W is a wall. W2 is one of the walls of the full polytope on the face W1. See, it doesn't have to be, right? You have a wall here, you have a lot of other walls far away. When you go to this wall, only a fraction of all the walls of the polytope, all the faces, are actually faces of the one that you start with. Okay? So W2 is a face of the polytope on W1. W3 is a face of the thing on W1 and W2, and so on. Okay? So that's a permissible path in the W's. And the symbol of this function of polytope 1 and polytope 2 is simply the sum over all the permissible paths in V and W space of the first term is just V1 dot W1. The next term is V1, V2, W1, W2. The next term is, and so on, up to the end. Okay? So that's a beautiful formula for the symbol of this generalized symbol of the generalized Aomoto polytopes. I won't derive it for you, but it has a quite simple, a very, very simple derivation and reason why it's true. But what I want to point out here is that the actual formula is a one-liner, but if you give me two complicated enough polytopes that actually stare at the symbol, I would never see that it's simple, right? Because there's zillions of paths, and if you actually just expand it out, you're not going to see that it's that this is actually what it looks like. Okay? So now, essentially, exactly this formula works for cosmological polytopes. Okay? The only difference is that because I'm not integrating over all the variables, but only the variables that are associated with the vertices, that I actually have to, I write this whole thing down, but I ignore the first bunch of terms. I ignore the first bunch of terms given by the number of edges, which are the things that I'm not integrating, and then I start. That's it. Okay, so I just lop off. I lop off the first part, and I keep keep going. Okay, so and it's still true that I sum over all paths, but I just lop off the part of the symbol that has E, the first E entries of the symbol. Huh?
Why is from this side always?
Because it's because this method is really coming from the differential. This is very obvious. Yeah, it's because one way of having frozen those integrations is as if you had taken differentials on them already. Okay, so it's really as if I'd taken a bunch of differentials in the edge variables already, which is why I lop off the first k of them. Okay, so in the end, to write down the symbol associated with this answer, you start the cosmological polytope and you just make walks on this thing, right? You just walk, ding, 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 ding. For every walk that you do, you write down an entry of the symbol. And I mean, it works. It's right. It's correct. But again, if you don't have this picture for it, already that the symbol for that the trilog that you get for the 5-point guy is like 105 terms in it. It's not very complicated on the scale of things that symbologists do, but you would not guess that it's just this one. Really this one-line expression, right? So the cosmological polytope is capturing everything about even the branch cut structure of these interesting objects. Okay. So anyway, the summary is that I think it's clear that there is some extension of these geometric ideas also to these cosmological situations, but this is a very primitive state of affairs. Okay, we can do it one graph at a time. You know, we don't even have, I think the biggest open problem to me is to figure out, even for phi cube theory, for tree graphs, if there's a way of combining all of them together. And I have to say, one of the funny things in this story is that earlier on, when we ran into these objects, something that bothered me was that the cosmological polytopes had a difference in them compared to scattering amplitudes, that they lived directly in the kinematic space, whereas the amplitudes lived in the Grassmannian or on the world sheet or in other places. Okay? And it's kind of funny, it was that our understanding of amplitudes changed and came closer to what we were already becoming familiar with from the polytopes. Also here, I had no idea how to imagine combining these things together. They naively live in different spaces. The graphs live in different spaces. So it's not even clear how to combine them. Exactly the same complaints in words about how you could never combine cubic graphs together to make a geometric object. That's the problem that was solved by this subspace idea in the story of the icosahedron. So the hope is that there's some way of thinking about all of these pieces as actually gluing together in a larger kinematic space into some analog of the icosahedron. That's got to be some pretty fancy thing, because already, even I'm doing from tree graphs, the simplices for amplitudes are turning into cosmological polytopes, piece by piece in this story. Okay, but there's actually already a 0th order challenge. Forget about the full cosmological polytope. Just go to the face where you're supposed to reveal the amplitude. See, on that face, the way the amplitude comes out is different than we're used to, precisely because of this business that all the poles are doubled, right? So that's already a simpler version of the problem. There it should literally reproduce the story of the icosahedron, but somehow in a twice as big space, with twice as many variables where the propagators are doubled. And so already there, we should try to figure out if we can combine them together, what it means to combine them together, and so on. I think, to me, the sort of excitement of this subject lives or dies based on whether that can happen, because it would be such a pity for it not to be possible that I would think that that's a sign from above that we should not be pursuing this particular line of inquiry. But I think if it does happen, it would be very, very exciting. Let me say one final speculative thing about why it would be exciting. You know, we've gotten used to this connection between the world sheet and scattering amplitudes, and of course, with string theory to begin with, excitingly with CHY and scattering equations in a different way, but still the same worldsheet structure, right? So there's something where the object was sitting there, and there was an old way of doing it, there was a cool new way of doing it, but the object that it was related to was sitting there. Now, there is something that string theorists have struggled with for many years, which is to figure out what the analog of the worldsheet should be in any workable way for cosmology, for de Sitter space, or even for ADS correlators, boundary correlators. And at this level, since we're talking about conformally coupled fields in the bulk, we could also be doing ADS correlators. It doesn't really matter, okay? So let's say there is, this is another fantasy. Where's the guy making fun of me? He's gone, all right. There's another fantasy, which is that that there is some kind of associahedron, some geometry for the full object for phi cube theory, say, okay? But then if we find it, we should find its worldsheet, the analog of its worldsheet that pushes forward to it, okay? And now we're not just borrowing things that existed for a long time ago. We're actually seeing something about the structure that could be also useful. So we would have the analog of scattering equations, we could hope, or wave function equations, whatever you'd call them now, that takes us to this new worldsheet prime. And then we could hope to figure out what the Kobe-Nielsen form of it is. And that would be something revolutionary, I think, if that form existed, because that formula does not exist after all these years. There is no 4-point, stringy 4-point function in ADS space. Nobody has a formula for this object, okay? In principle, there's a worldsheet theory for ADS5, but no one can calculate anything with it. It's not a calculable weakly coupled theory. So it would be fabulous if we could carry all of this program through with amplitudes backwards, because now we'd be discovering something new at every step of the way, and a new kind of worldsheet perhaps, and the kind of worldsheet that's relevant for cosmological calculations and for even calculations of boundary correlators in ADS. So there's been a lot of fantasy after midnight tonight. Call 1-900, future boundary. Yeah, see, I don't even know enough to complete that perverted line of thought. But anyway, that's, I think, what would be one of the most interesting things that could come out of pursuing this line of thinking. Independent of the connection to geometry, I'll say just a final thing, that these wave functions, or cosmological correlators, if you calculate them for n equals 4 super Yang-Mills, they're just the same as a flat space wave function. The theory is conformal, so it doesn't even care about whether it's flat space, ADS, de Sitter. This is a beautiful object that nobody gives a rat's ass about, okay? Formal people don't care about them, amplitudes people don't care about them, cosmologists don't care about them, nobody cares about them. I care about them. I think they're great, because they are a one-parameter generalization of n equals 4 super Yang-Mills scattering amplitudes. And they have to be spectacular, okay? They have every right to be fully Yangian invariant, no infrared divergences, nothing messing them up. There's just nice, clean, beautiful objects. And nothing is known about them. There's a tiny amount. Suvrat Raju wrote some papers where he calculated the 4-point tree correlator, or maybe some 5-point one. Apart from that, nothing is known. So I think this is not something I'd encourage a student or a postdoc necessarily to work on, because really nobody cares at all. Okay, like nothing at all. But I think they should care. So it's just an advertisement. If you feel like giving a middle finger to the establishment, you can spend 6 months calculating the wave function of n equals 4 super Yang-Mills in perturbation theory. So, all right. I think yes. Yes, we can take the last break. Yep.